Hello everyone, my name is Nicholas Tercios. I'm one of the team leads for the collaboration between UAVs for the Fire Detection and Suppression Senior Project. And today I'm going to be going through some of the design with all of you. So a quick overview of what this presentation entails. We'll start off with the project objectives, following with some of the motivation behind the project. We'll transition to our key design requirements that we set for ourselves as a starting point. We'll then go into the concept of operations, talk a little bit more about the test vehicles we're planning to use, and then talk more in depth about our detection system, our suppression system, wrap it all up, and then talk a little bit about what we want to do next year. So what were the objectives for this project? We wanted to develop a collaborative mission that was able to use two UAVs for fire detection and suppression. We wanted to integrate a UAV with a fire suppressant dropping mechanism that could also interact with the environment around it using a mechanical arm. And we wanted to see if we could verify the overall design via extensive simulation and flight. As for the motivation behind this project, UAVs have a lot of potential to be used for fire detection, monitoring, and suppression around the clock. They can stay in the skies longer than we can stay awake, and they can be constantly switched out to make sure that we are always on top of the fire. At the same time, collaboration between multiple UAVs can be very effective against detecting and suppressing large fires in large areas. The UAVs can also be used in collaboration with firefighters and provide critical information to them, again, around the clock. They will always be in the air, constantly monitoring our fire of interest. Last but not least, UAV can also be equipped with a robotic arm that can be used to extract objects in these hazardous locations. Think about removing debris, assisting a firefighter in a hazardous situation, etc. So here we have outlined some of our key requirements. For the detection and the suppression UAV, you will see that there is some intermingleness between the two. We want to make sure we can operate from at least 350 feet away. This is where we're planning to do a safe distance and hope that we can expand this in the future. We also want to be able to detect a fire and suppress a fire at an altitude of at least 30 feet. The fires that we're planning to suppress and detect must be 10 feet squared at the minimum. And for the manipulation part that I hinted at earlier with the robotic arm, we want it such that the robotic arm can be used via a VR controller and a headset, so that way you could see it with stereoscopic vision, the area of interest, and you could control the movement of the arm with the controller. We also want to make sure that this arm is capable of interacting with objects weighing up to 5 pounds. So here we have the concept of operations. I will start on the left side with the manipulation mission featuring the robotic arm I just mentioned. So we will have a manual takeoff, and we will manually fly to an area of interest where we will interact with objects such as debris. We'll try to pick it up and move it into a different location. We want to also manipulate objects such as levers to show that we can interact with more man-made materials. And last but not least, we also want to show how we can interact with objects of interest. Think, for example, a briefcase in a hazardous spot that we would want to get out of a burning building. We want to pick up this item and also bring it back to our ground station. On the right-hand side, you'll see two missions, the first being the detection mission. This is part 1 of 2. It will begin by taking off manually, but then switching to an autonomous mode where it'll autonomously search a predetermined area. Along the way, it'll avoid potential obstacles and search for fires. When the IR camera detects a fire, it'll store its GPS location until it has swept the entire area, and it'll return to the ground station. Once it returns to the ground station, we will take the GPS coordinates and feed it to the suppression UAV, which will feature a manual takeoff, autonomously fly to the fire, and then we'll deploy the suppressant. It'll then return to the ground station.
The next, we'll talk about the test vehicles that we have used. So for the detection, we use the DJI suppression. Actually, we use the DJI Matrice 600, and with the following specs shown on the right, and with equipped the DJI A3 flight controller. Then with the detection, we use the DJI S1000 with the specs shown on the right as well, and used the Pixar 2.1 flight controller. And then specifically then on the flight controller, So the suppression UAV using the A3 has a compatibility with the arm supporting and the motor fail detections and protection, and as well as the propulsion protection. It has already been integrated onto the UAV and is waiting for the production and assembly of the parts. And for the detection UAV, the PICSOC was used. Originally, it was supposed to be the Dimitri 600, but due to the fact that we faced compatibility issues with its motors, we have switched to the S1000. And so for the future work we would like to assign members to purely devote on integration of PICSOC and Dimitris together and investigate on this issue and have it successfully integrated eventually. And once that integration is complete, then we can have the implementation of the obstacle avoidance algorithm into the controller and test its capabilities. So then for the detection system, first the fire detection algorithm. So for each frame, a signal was generated and went through a high pass filter and a high pass variance, and then the intensity was found using the sum of the total number of pixels from 200 to 255. Then in the video, we then had look for the variance of each frame, and drastic change in variance and high variance was looked for. And with higher concentration, that we would then mean it would mean that we have detected a fire. So for the no fire situation shown in figure 8, 9, and 10, we can see that figure 9, there's a low intensity with numbers being around 2000s, and as well as for figure 10, that there's low variance and less drastics. And then for a no fire to fire situation, which normally means that we detect the fire, we see in figure 11 and 12 and 13, we see that there is a low to high intensity showing that the threshold goes over 5,000 in figure 12, and as well as the large variance in numbers for figure 13 as well. And so in the future works, we would like to take into account of other heat sources other than fire, such as humans and animals, and also have a program for fire non-fire equation of the intensity threshold, drastic variance change, and large enough variance. And then for fire location determination, so using the thermal images that we have received, then given the pixel coordinates of the fire, we then calculated its location relative to the camera, and with this results shown. And we can see that location 1 has very good results, but for location 3, it has some slight error there, and possibly due to the camera specs of the angles of it, the local wind, and errors from image processing step as well. And then finally we have the obstacle avoidance pathing system, and it was tested in GUI and showed promising results and worked on integrating algorithm and drone kit together. In future works, since we would like to work on a conversion algorithm between DroneKit and LiDAR, since DroneKit uses GPS coordinates to navigate, while the LiDAR uses 3D plane to relative to itself. And we then want to work on increased efficiency of algorithm to process large sets of data.
So moving on to an overview of our detection sensor system. First, we have the S1000 sensor mount, as shown in figure 1. This will have the VLP16 LiDAR. In figure 2, we have the Matrice 600 sensor mount. This will have the VLP16 LiDAR, an Intel processor, an IMU, a FLIR Tau thermal camera, and a LiPo battery. Figure 3 and figure 4 show each sensor mount integrated with their respective UAVs, the S1000 and the Matrice 600. For the fabrication of these mounts, we 3D printed them using PLA plastic filament. Originally, we were going to use carbon fiber PLA as it was stronger, but it caused a lot of burner issues, including extruder clogging and straining, so we switched to regular PLA. Here in figure 1, you can see the Matrice 600 sensor mount with its sensor front view, its left side view, and a front overview. And as you can see, it's been modified to have no LiDAR, and the rail slots had to be widened so it would fit the Matrice 600 rails. In the future, this sensor mount is going to have to be remodified to integrate the LiDAR for mapping purposes. In figure 2, we have the S1000 sensor mount, both assembled and disassembled. This mount will, again, only hold just the LiDAR, and in the future, this whole system must be transferred to the Matrice 600 after the Pixhawk 2.1 integration is complete. So now moving on to the Suppression UAV, here's the robotic arm fabrication. The arm was fabricated successfully, all servos were attached, and full control was verified through static testing, as you can see on the right. The gripper still needs to be attached. Here's a look at our gripper subsystem. It will be integrated with the robotic arm, and it is actuated with an HS422 servo. The overall goal of the gripper is to grab and hold up to a 5-pound payload and hold the object for an extended amount of time, about 20 minutes. This will simulate the removal of debris from a fire situation. So for the modifications that were made on the gripper, some of the components were redesigned, such as the servo placement, the claw limb, and the gear key or shaft. It now uses an HS422 servo, as you can see the changes on the right. A final stress analysis test was also completed, and fabrication and integration of the gripper was then completed after that. The gripper was controlled by an Arduino during testing, and it used a potentiometer to actuate the fingers. As you can see on the right, it held a battery with a weight of 1.18 pounds, with the servo grip strength being the main limiting factor. Now here's our main suppression system. It has a bucket design with a funnel shape that can turn inside out. The bucket is a fabric made of neoprene, and the frame is made of Delrin. The whole system is designed to hold 1 gallon of water. The mount is also made of Delrin, and it fits onto the bottom of the Matrice 600. For the future, a different material needs to be chosen since Delrin can melt and isn't suitable for a fire situation.
So here we have the microcontroller for the Suppression UAV. We have a conditional PWM operated servo controller, and the board can output any arbitrary number of PWM signals. However, we have programmed it to output a maximum of 3. Some things we want to do in the future is go with RF transmission. We don't want to have a ground station, so we want to use RF transmission to mitigate that. Moving on to the next slide. We have our power distribution model. We have 1 battery for all of the components and step-down converters for the required voltages of each component. We have tested all of this using an Arduino and ensured the voltages were correct for each component using a voltmeter. Some things we want to do in the future is add a kill switch, most likely software, however hardware would possibly work as well. Moving on. Here is a visual representation of the power distribution. On the left-hand side, you can see how it is all situated and where it is located on the actual drone itself. And on the right-hand side, you can see the power distribution model in action. In this picture on the right, we actually have a breadboard instead of a soldering board. However, that has been changed. Moving forward, we have our VR vision and control for the fire suppression drone. We have a virtual reality headset and a program in Unity 3D to control the components of the UAV from a distance. We have a stereoscopic camera that is mounted on the UAVs that we can have our 3D vision, and a virtual model of the robotic arm in the actual Unity 3D program. Moving on. We have our VR interface with our Oculus headset and a SolidWorks model of the arm and camera. The camera is connected to the program and is functioning, and our inverse kinematics allow us to control the model of the arm. It has been accurately modeled to the arm and gripper rotation limits, and the data is exported through a COM port. We have tested this and verified it. However, we have reduced the sample rate of data to prevent a low frame rate so that we can have a higher frame rate and a more clear view in the VR headset. Moving on. In conclusion, we built a detection UAV that detects and locates fire using an algorithm with a thermal camera and a LiDAR to navigate around obstacles. We also have a suppression UAV that has a robotic arm and a gripper with a VR interactive interface, or a suppression system with a gallon of water in a neoprene fabric bucket to disperse on a target. So some things that need to be done in the future. We want to test and validate all our current components in a flight test and update the hardware components with improved designs as we move forward. we want to reintroduce the LiDAR mapping as mentioned previously and continue our development on the detection and geolocation algorithms. Furthermore, we want to implement RF communication so we don't need a ground station for autonomous missions. Lastly, we want to possibly maybe move to only using one UAV, but doing this would mean that we would need to increase our size of our team and sub-teams to spread the workload. Lastly, we want to develop and expand the schedule and budget for the following year. Now, I'd like to thank our mentor, Dr. Bhandari, for his generous support of this project. Thank you.